Good evening, everyone, and welcome to tonight's lecture from Mars with Love, Postcards from 50 Years of Exploring the Red Planet, which is the second of Chris Lintott's series on the state of our universe. Before we start, a few housekeeping notes. If there's a fire alarm, it's not a drill, it's for real. So there's 3 exits, one here, one there, one over there. So please calmly make your way to the exits, and outside we'll have team members helping you find the meeting point. The other thing is, as you will know, we have a Q&A after the lecture. You can either raise your hands when you're in the hall, and 2 microphones will be roving around the hall, and please wait till you've got the microphone. Be brave, speak into the microphone, ask your question. If you're online, then please use the QR code that you see on the bottom right of your screen. If you're in the hall and you don't want to raise your hand, you can also use that. You've got all on your seat the booklet, and at the back there's the QR code, so those of you who would rather ask the question online, you can do that. The other thing is, I'd like to take this opportunity to thank everyone who's already contributed to our Christmas fundraising drive. You might have seen these leaflets. From today until next Tuesday, all donations will be doubled, and any donation, small or large, is much appreciated by the entire team. So thank you very much for not just supporting our lectures by being here and for making the hall really full, but also contributing. The other thing is, I promised a shout out to St. Benedict's School from Ealing. Can you give me a whoop whoop? Oh. We have to practice that. I'm really sorry. But anyway, so part of our schools program is here today, so we're really glad to have you here for tonight's lecture. So let me introduce Professor Chris Lintott. He's the 31st Gresham Professor of Astronomy. He's also Professor of Astrophysics at the University of Oxford and a Research Fellow at New College. His research ranges from understanding how galaxies form and evolve to using machine learning in order to find the most unusual things in the universe, and also includes predicting the properties of visiting interstellar asteroids. He was the founder of the Zooniverse citizen science platform, which provides opportunities for more than 2 million online volunteers to contribute to scientific research. And to a lot of you, he's just the guy from Sky at Night on the BBC. So please put your hands together for Professor Chris Lintott.
Thank you. Thank you all very much. Before I get started, I want to say that a lot of the things you'll hear about tonight are the work of people at NASA, and in particular at the Jet Propulsion Laboratory, lots of whom have just lost their jobs due to the situation in the States. So I want to dedicate this lecture and everything that we've learned about Mars to them. But thank you. Thank you. Thank you. If they're watching online, they can send me corrections later. I'm really excited to be talking about this topic tonight. 50 years ago, the first 2 spacecraft that would go on to make successful landings on the surface of Mars, our nearest neighbour, 4th planet from the Sun, the most Earth-like of the worlds that share our solar system with us. Those first 2 spacecraft were already on their way, and they would touch down during the Earth summer of 1976. And those probes, known as the Vikings, kick-started a on-off series of exploration missions to the Red Planet that have transformed our view of it and a little bit our view of Earth. And along the way, they've entertained us, intrigued us, and basically produced fantastic images like this one that I heartily recommend spending time diving into. This is an image from a rover that I'll get to later on, one of the rover Curiosity. And what you can see here is a valley on Mars. And what I think speaks to me about this image in particular is that it could well be Earth. There's something about this that puts you in the picture. I think it's the fact that on a lot of these rovers, the cameras are about 2 meters above the ground, so they produce a roughly human perspective. And if you're a hill walker like I am, you can imagine plotting your route through this valley. If you're a climber, I imagine in your minds you're already halfway up the half-foot at the back. And if you like a picnic, well, this is quite a good spot, apart from the lack of atmosphere, etc. These images have helped us understand Mars as a complex world. And some of them have put that position into perspective. So for example, this is another image from Curiosity. This is a nighttime view. The sun has just set over the Martian landscape, and you can see, hopefully, about a third of the way across, there's an evening star in the Martian sky. And if we zoom in, we can see that's a double star, and it's double because that's the Earth and the Moon, as seen from the surface of Mars. So that's us from the perspective of one of these Martian explorers. And the reason I'm showing you this tonight isn't to do the Carl Sagan thing of spending the next half an hour going, remember, everyone who's ever lived existed on that dot, though that's true. It's to point out how absurd what the scientists who've worked on Mars and what I'm going to try and do tonight is, which is imagine that that's the view we have of the Earth. Imagine that you have that view, and then you get to land 10 times at nearly random places on the Earth's surface. The most you travel is about 30 kilometers from any one of those landing sites, but most of the time you stay put. And then imagine trying to write a history of the Earth. Even just a geological history would be extremely hard, and yet that's what we're asking of our understanding of Mars. And so what I'm going to do, rather than try and give you a beginning to end story, because we haven't written that yet, what I'm going to do is give you a series of postcards from 10 missions that I think have been particularly influential. Most of the missions that touch down on the surface, but also a couple of orbiters, to give you a picture of where the questions and the complexities about our understanding of Mars lies. So let's start with those Viking missions. The postcard I received from Viking says, "Dear Earth, from orbit, Mars looks like a fascinating world. We knew about the ice caps and the high desert from observations made at home, of course. But what's clear up close is that the surface has been shaped by liquid, most likely water. There are what seem to be river valleys hundreds of kilometers long, and whole parts of the planet which seem to have been affected by flash floods of unimaginable scale. On the surface, the atmosphere seems to change with the seasons, the air pressure rising as carbon dioxide sublimates from the polar ice caps in summer. But regardless, it's always dusty." This is going to be a recurrent complaint from our missions. "The sky seems pink with the stuff, and it gets everywhere. I did test for life, like you wanted, and the results are confusing. Best tell everyone at home that there's no conclusive evidence, as I'm sure that will satisfy them and in no way produce 50 years' worth of debate. Yours, Viking." Okay, so that's an overview of the missions. Viking 1 arrived in this is a shot. This is a mosaic of Mars from Viking 1 from 1980. And so this is sort of the view you'd get if you were 2,500 kilometers up. You've got the beautiful Valles Marineris, Mars's answer to the Grand Canyon, which of course dwarfs our own, at the center. You've got the volcanoes, those spots on the far left, the great Tharsis volcanoes, and you have this sense of a desert world. Now, Mars is about a tenth of the mass of Earth, so it's a small planet, it's about half the size. But because it doesn't have oceans, the land area is about the same as the Earth, and we have all the diversity and variety that we see on Earth. In particular, you can contrast the low latitude areas with the dramatic polar caps, and the Viking orbiters told us lots about these polar caps. This is an image of the North Polar Cap. This is a system of water and soil, so water, ice, and soil, covered with a water cap, and then there's dry ice, CO2, that freezes out seasonally onto the polar caps. And Viking discovered that 3 to 4 trillion tons of carbon dioxide transfer from north to south as the seasons on Mars change. If you took all the water that was in the polar caps and covered the surface of Mars, Viking tells us that you'd get an ocean that was 20 meters deep. And so one of the things that was important about this mission in particular is that it told us that though Mars is a desert world, there's no running water there now, there's no rain, there's no nothing that we'd think about when we talk about the water cycle on Earth. There is water there, it's just locked away in freezing cold conditions. Viking also told us that it's a dynamic place. This is an image of a dust storm moving across the Martian plains, and we'll come back to those soon, so that The dust that's pervasive on Mars scatters into the atmosphere, is heated and kept aloft and travels around the planet. And of course, the most famous Viking discovery was that there's a face on Mars. It does look very convincing, yes? Future missions took a picture of this feature. I'm afraid it's not a face. But it would be nice if it was, right? It's definitely not. I really want to talk about the landers as well. There's a brilliant 1970s animation of the whole process of getting to Mars that I'm just going to let play. But the big thing that this mission tried to do was what had never previously been successful, which is to land complex machines on the surface. Viking 1 touched down on July the 20th, 1976, which is the 7th anniversary of the moon landings. That's how quickly things were moving on. And the challenge, Mars is really interesting. It's actually a harder place to land on than the moon. Because if you're trying to put a spacecraft with people in or a robotic spacecraft onto the surface of the moon, you don't have to worry about an atmosphere. You can just use rockets to lower yourself to the surface. And while you need nerves of steel, if you're Neil Armstrong or Buzz Aldrin to do that, it's technologically doable. If you're landing back on Earth, maybe having been to the moon, then you can use the Earth's thick atmosphere as a brake and slow down on your re-entry using our atmosphere. Mars has enough atmosphere that you can't just use rockets, but not enough to slow you down from interplanetary speeds. And so it's almost the worst of both worlds. But the Vikings managed to touch down under their own power, and this was the first image ever sent back from the surface of Mars. It's sort of a proto-selfie showing the Viking rover's foot and some exciting rocks. Viking 1 lasted for more than 6 years until somebody accidentally sent a command telling it to shut off, which is one of the sadder ends to an interplanetary mission. And Viking 2, which landed in September of 1976, carried on for 3 years until its batteries died. The main discoveries from the two were that the soil of Mars is extremely rich with iron. In fact, it's stuck to magnets. And that's both because it's of the presence of a mineral called magnetite, but also the redness, which we often talk about as rust on the Martian desert. The redness is a mineral called hematite, an iron-rich mineral that forms in slightly mysterious circumstances and is blown around the planet. It was also a complex mix of other elements, carbon, nitrogen, sulfur, all contained within the soils of Mars. The experiment, these are artists' impressions, obviously, in the top left. The experiment that people remember from the Viking missions were carried out by this rather complex device shown here. Viking is the only mission to date that explicitly tested for life on Mars. So it dug up soil, it put them in this series of ovens, and they carried out a series of experiments. For example, heating the soil and seeing what came off from it. They also did what's called a labeled release experiment, where they put radioactive carbon into the soil, with the idea being that if there was life there, it would process that carbon, if you could think bacteria or something like that, and they'd be able to see what gases were emitted. The results were somewhat controversial. I think 2 of the 4 tests were unambiguously negative. The other showed that there was some reaction happening within the soil, but it died off quickly over time. So it wasn't like you'd fed some bacteria and then they'd prospered, and then you'd got more life, so you'd expect a stronger signal over time. So NASA reported this, as I mentioned in the postcard, that there's no conclusive evidence for life. And this was, in some sense, a surprise. Though the science fiction Mars of canals and little green men and intelligent civilizations living in crystal cities had long been forgotten by this point. The first flybys had shown us that there were no such things on Mars. I think most people thought primitive life was likely. And yet Viking failed to produce evidence, at least for abundant life. And that sat things back for a while. At the end of the Viking mission, it was more than 20 years before anyone returned to Mars. I remember talking to the head of the Mars program at JPL towards the end of that time, and he was explaining that this is why you build expensive missions, because you need to collect enough data to keep you busy for the 20-year gap until you can get funding to go back. It's a slightly tongue-in-cheek and cynical view, but it was certainly true that I think the failure to find life really cut off interest in the Mars program. It was almost as if they'd done one test in one place and they decided there was no point going back. As we'll discuss, I think there are plenty of reasons to go to Mars other than looking for life. So let's take a completely different mission. I'm not going to do these in chronological order, but let me tell you about my favorite Mars mission. This was a mission called Phoenix, which landed in 2008. It was a much smaller, lower budget mission, a static lander on the Martian surface. It actually went to the Martian Arctic, and we might pretend it sent back a postcard. Dear Earth, firstly, it's cold. Very cold indeed, and it's even snowing. There's dry ice falling from the sky. It's also windy, though the thin Martian air doesn't pack much of a punch. The landscape is peppered with small rocks, and the freezing and thawing of the soil around me has split it into weird-looking polygons. You wanted me to look for water? Well, it's here, just as we thought it was from orbit. The soil is full of the stuff, and when I heat it to 0 degrees Celsius, it boils. But the acidic soil has another surprise. It's full of a chemical called perchlorate, bad news for life, and which may explain Viking's odd results all those years ago. Got to go, winter's coming. Phoenix. P.S. Thanks for the DVD, you forgot to send a player. This is Phoenix. This is where it landed. So this is a selfie from the surface. This is the DVD that was sent, which contains footage of Earth and the names of about several million people. No instructions on how to play it, so whoever recovers it better still have a DVD player knocking around. Phoenix, as I said in the postcard, went to a special place. It was the first mission to land away from the equatorial region of Mars. It's easier to go to the equator, but Phoenix landed in the Arctic, a place where the temperature varies between about -20 and -80 degrees centigrade in the middle of the summer. And its mission was to establish that there really was lots of water here in Mars. It's the epitome of what NASA thought of as a follow-the-water strategy. Rather than trying to find life directly, start by trying to find water. The great thing is that Phoenix pretty much instantly achieved its mission. As it landed, its retro rockets blew away some dust, and there was some white material underneath the lander. In fact, here's a scoop taken on the 20th Sol, or Martian day, of the mission. You can see there's ice here. That is water ice. I was in mission control for this discovery, and I'm pleased to report that the team celebrated as an Arizona-based team with margaritas, because they felt that they'd discovered ice and salt on Mars, so they had 2 of the 4 ingredients down. It's a very bizarre experience. This mission was going to be short-lived because of the seasonal changes. It was expected to get very cold, and in fact, they hoped to see a wall of ice approaching Phoenix as the polar cap expanded. And so the team wanted to make everything they could out of being on the Martian surface. And so they lived and worked on Mars time. A Mars day is 24.5 hours long. And so that meant they slipped by half an hour in time zone every day compared to the rest of the world, compared to their families and so on. And for about 6 months, lots of them lived like this in accommodation and offices that were blacked out so that you couldn't see earthly sunshine and have your body clock reset. It was a really wonderful mission. They found their water. They confirmed that what we were seeing from water really was water ice, so that we go back to this idea of Mars with hidden reserves of water. They also took a surprising amount of delight in measuring the weather. Here on the left is my favorite experiment ever sent to Mars, mainly because I like really low-tech things. This is how you measure wind speed on Mars. You have a webcam pointing at a weight hanging from what looks like a jury-rigged bracket, but I assure you it's not. The wind speed was about 6 to 36 miles per hour over time, but as noted, the thin Martian atmosphere, even when you have very strong winds, you could stand up easily. It's no threat to machinery or man. In fact, it's the one thing wrong. If you've seen the film The Martian, the dust storm and the storm that puts the crew in peril is utterly unrealistic. And the author, Andy Weir, admits that this is true. It's the one thing he changed for dramatic purposes. On the right, this is a laser firing upwards from the Martian surface from Phoenix. And this experiment was designed to test the presence of clouds and other particles in the atmosphere. And it was this laser that discovered that in this part of Mars, it snows. It snows dry ice. And though we didn't get to see the onset of proper winter, this snow was beginning to accumulate on the ground in a sort of Martian Christmas scene when the lander ran out of power, 157 sols, Martian days, after its beginning. So Phoenix really confirmed what Viking had told us long before, that we had a world in which there were reservoirs of water and ice. But before that, we had the robot geologists. And I think the mission that really transformed people's view of Mars was called the Mars Exploration Rovers, partly because I think they look jaunty and interested. There's something very pleasing about the design of these things. I think it's the eyes on the two eyes on top of the camera and the can-do attitude that's somehow conveyed by the 6 wheels and the robot arm. This was a scientist mission. I'll say a little more about the principal investigator, Steve Squires, in a second. But one of the things I really like about this mission is that in its design, whenever you design a mission for a space agency, you have a list of objectives. Check that there's water on Mars or whatever it is. Get to the surface safely might be one. And you have an acceptable tolerance for risk. So you might say, okay, we need to get to the surface, and for this particular mission, we need to, with our engineering, get to the point where we think there's a 98% chance of success. And that's difficult in a mission where you have single point failures, where you need a parachute to work or antenna to operate and so on. And Squires and team realized that there was a cheat code, that instead of making every part on a single rover as reliable as it needed to be, they could just build 2 rovers for the same price. And therefore you could accept more risk, because if you lost one, you got the other. But if you were lucky, as it turned out, you get 2 missions for the price of 1. So let's take them in turn. Let's start with Opportunity. This is an artist's impression. I really like this as an image. This is its shadow on the Martian surface. Landed in 2004 in January, just after the European British probe Beagle failed to successfully transmit a message from the surface. And the postcard from Opportunity says, "Dear Earth, hello from Mars. After a bouncy ride to the surface, I was excited to see rocks. And what rocks they are, rich in blueberries. Not actual blueberries, you understand, but spherical concentrations of hematite which must have formed in water. Not exactly water good enough to drink, though. To form these things, it must have been as acidic as sulfuric acid. What I don't know yet is if the water on ancient Mars flowed freely or if I've landed in what's left of a stagnant pond. There's plenty of science to do. Time to get some dust under these wheels and explore a little. My arm does feel a little creaky, though. Hope that's not a long-term problem. Onwards, Opportunity." Spoiler alert, the arm on the front of the rover broke pretty quickly, and it spent something like 10 years driving around with the arm bouncing in front of it, which I think just adds to the general sense of adorableness. I've talked about the difficulty of landing on the surface. Opportunity and its twin Spirit used a new system which seemed complex but worked. You enter the Martian atmosphere, you deploy a parachute. As you get near the surface, you get dropped from that parachute, but you get dropped inside an inflatable airbag. This is a scaled version of it. This is the life-scale version of this thing in the Mars yard at JPL, and you bounce to a stop. And the delightful thing about Opportunity is that it bounced to a stop inside a crater that was 22 meters across, which was claimed by the team as the first interplanetary hole-in-one. I think it's cheating if you don't know you were aiming for the hole, but sure. What really excited them was that you can see in this first image, and that's the airbag in the foreground deflating gently. You can see in the top right of this image that because we're in a crater, and this will have been a crater that formed when something hit the Martian surface, you can see there's rocks exposed, bedrock, not just soil, but rocks in situ, a geologist's dream. And Opportunity quickly went on to study lots of those rocks, and you could tell that they studied them carefully because they started to give them all sorts of strange and interesting names. There's Phoenix, Guadalupe, Shark Fin, you can imagine how that got its name. But the one that became notorious was Berry Bowl, because these rocks, which are layered, so they were laid down over time in a process that produces layers of sediment. So that's either waterborne, so you get a flood maybe, and then some mud that sinks down, and then flood, mud, and so on, or perhaps a sandstorm-like process. In fact, we think these were deposited by water. In the berry bowl, there were berries, as you'd expect. These are tiny spherules. These spheres are about 4 millimeters across, and the circular patch in the middle is a place where the rover was able to drill just a little bit into the surface. And the spherules have a different composition from the rock underneath. And this is the kind of thing that forms within a long-lived, iron-rich pool of water. And so this is direct evidence that this part of Mars had water, liquid water, which existed for a long period of time on the surface. It wasn't just a flash flood. So this is the first evidence that ancient Mars, and we're probably talking at this point more than 3 billion years ago, had lakes, had ponds, had pools of water. But the chemistry of the minerals that we're seeing here and in neighboring craters like Endurance that Opportunity went on to study, the mineralogy tells you that this would have been an acidic conditions. So these would have been places where you had water, but it would be about the same acidity as the sulfuric acid that you'd have on a lab bench in a school chemistry lab or something like that. Very unearthly conditions, certainly not the kind of conditions you'd want if you were thinking about life. And this is where I learned a really important lesson about Mars. At this point in the mission, I was interviewing Steve Squires, the principal investigator. Now, these missions, Opportunity was supposed to exist on the surface of Mars for 90 sols, 90 Martian days. And at the time I was talking to him, they were 2 years into their 90-day mission. And so I remember the first question I asked him, which is, you're 2 years into a 90-day mission, how do you feel? And he said, tired. And then didn't say anything else. And then we got talking about these results, and I expressed a mild disappointment that we'd found only evidence for acidic water on Mars, because obviously I was thinking about going to Mars and finding places where life, Earth-like life, might exist. And Steve looked at me. I don't think it was contempt on his face, but he was certainly tired. And he said, look, we don't go to Mars because it's like Earth. If we wanted to study Earth, we'd stay here. We go to Mars because it's not Earth, and so when it's different, that's good. And I think that's an incredibly valuable lesson, not just for people studying Mars, but for science in general, that we look for places that are unlike what we have here, because that's how we learn. Opportunity went on to travel an enormous distance. It set a record roving across the surface. I really like this image in the bottom left, which shows it on the edge of a further crater, Victoria crater. This is an image from orbit where you can see the tracks of the rover and the rover itself on the edge of a cliff. But over time, over a very long time, it began to lose power. Like a lot of these missions, it relied on solar power. This is an image from early in the mission in 2004. This is a selfie taken with the camera on the end of the arm. So that's why it's sort of a self-portrait. This is from near the end of the mission. This is not a solar power system in good health. One of the reasons the rovers survived longer than we expected was because occasional Martian breezes would blow dust off these solar panels, and they'd get what the mission teams call cleaning events. But eventually, years after Opportunity landed on the surface, it lost power entirely because of this event in 2018. So this is 14 years into a 90-day mission. On the left is an image of Mars from early in the year. On the right is an image of Mars from orbit later in the year. And what's happened is that a global dust storm has blown up. These happen every few years, perhaps every decade on Mars, where small localized dust storms, where sand and dust have been blown up into the atmosphere, that process accelerates until the whole planet is covered for many weeks or months. And this is a simulation of what that would have looked like from the ground. So on the left is looking at the sun on a normal day through already hazy Martian air. And on the far right are the conditions experienced by Opportunity in the summer of 2018. And the rover lost power, switched off, and ceased communicating with us after a very long mission. But it had established that there was long-lived water on Mars, if acidic. Its twin, Spirit, had something of a more checkered landing. It didn't score a hole in one. In fact, when it landed, its memory failed to reboot, rather like my laptop, at the start of a week. And there were some problems, but it got going soon. So the postcard from Spirit reads, "Dear Earth, still recovering from all the hard work at Comanche, that small rocky outcrop with a lot to say. It's rich in minerals that must have formed in a warm and watery environment with no sign of the acidic conditions my twin has found elsewhere. These carbonate deposits might be 4 billion years old and prove that Mars was a very different place back then. Other than that, I've been enjoying spring winds blowing dust off my solar panels. It's very dusty here, as others might have mentioned, which has meant that this extended trip has lasted much longer than the 90 days I originally planned. My right front wheel is busted, which is literally a drag, but in the trenches it produces as I trundle along, we get a glimpse of what's under this endless sand. Still, it would be nice to be repaired. Yours, hopefully, Spirit." So this is the outcrop. This is Comanche, this red outcrop at the top here. This is probably the most important single site that we've explored on Mars. It is old, 4 billion years old, so it's older than the landscapes that Opportunity was trundling through. And as I said, it has minerals, particularly this carbonate, that must have formed slowly in a warm, watery environment at neutral pH. So this is evidence for the kind of pond you could happily swim in on Mars. And in fact, where this is located, if you look at this part of Mars from orbit, you see there's what looks like an enormous lake, larger than any of the Great Lakes on Earth. Then there's a channel, and this part of Mars is at the end of that channel. So we think that there was this large lake that eventually flowed down into this region and deposited these minerals. So we're learning what happened here. And that's confirmed by minerals like these white patches here. So this is what Spirit's rover tracks look like, because it's got 6 wheels, and it's literally dragging one along the soil. So it's scraping as it goes. These things move maybe a meter or two a day. So it's quite a slow process. But what's being churned up here is sulfur-rich deposits. So this might be a place that had a hot spring or something called a fumarole, where acidic steam is rising through rocks. So it's a place where you have water and then you have volcanic energy underneath. This begins to sound a little bit like the places that life got started on Earth. It's a chemically rich environment at the start of the Martian existence. Spirit got stuck in a sandpit in 2009 and lost power in 2010 and left its twin to go on. But these two rovers, as you might have gathered from my effusive introduction to them, really captured the attention. In particular, in their ending, really captured people's attention. There are many, but I'm really fond of this XKCD comic, which shows, I think this is Opportunity on day 1, being excited by 89 days to go before they get to go home, and then concluding that they haven't done a good enough job, and that they need to do a good enough job in order to come home, and then it must be Spirit, they get stuck and expire on the red planet. It's very hard not to feel sorry for the rover. A tendency that was exaggerated when a journalist reporting on the telemetry that Opportunity sent back as it lost power in the dust storm. It was all it could do at the end was report on its internal state. So, battery health, a bit like your phone, battery health, temperature, that sort of thing. And a journalist took this telemetry and explained to people that Opportunity's last message had been, "My battery is low and it's getting dark." Exactly. And then NASA spent weeks explaining that it didn't send that message precisely. But it does show, I think, that we get attached to these. These are voyages of exploration. And communities of millions of people around the world followed step by step these rovers. And it's still the case that for rovers that exist today, if you go to the Curiosity or Perseverance website at the right time, the mission teams make a point of not reserving any privileged access to what's coming down. So you can be the first person to see an image from Mars if you click refresh on the right web page at the right time. And we can follow along with these adventures. I want to make a brief mention of Pathfinder and Sojourner. So this is the 1997 mission that brought us back to Mars after a 20-year hiatus after the Viking. But this was essentially a demonstration mission. It was a time when NASA was investing in lower-cost missions. The principles were faster, cheaper, better, despite an old engineering nostrum that says you can only have 2 of those things, else things start to go wrong. And this strategy didn't work long-term, but it did get us this tea-tray-sized rover trundling around the Martian surface. And the postcard from these two says, "Dear Earth, we're very glad to be here. The great galactic ghoul has spared us. It may have been a budget holiday, but the ride was fine, and the view here in Sagan Memorial Station is great. There's dust sticking to all but one of my magnets, and in communicating with you, we've been able to find out that Mars has a solid iron core, which might explain the lack of a magnetic field. The weather's a bit of a worry. We've seen dust devils and surprising swings in temperature. Bigger solar panels next time, please. Love, Pathfinder and Sojourner." Pathfinder worked, it explored its surroundings, but the real impact of the mission was to study Mars globally. By having a mission on the surface communicating with Earth, we're able to study how Mars rotates over time. That solved a long-standing mystery, so let me explain. Here's a map of Mars. This is a map of topology. So color here tells you how high above, well, we'll call it sea level, but it's arbitrary on Mars, how high above or below the datum, sea level, you are. And you can immediately see that Mars has this unusual feature that the northern hemisphere at the top is much lower than the southern hemisphere. In fact, you can sort of split the planet into 2 regions. Why this will be, we don't know. But one possibility is that this is because of long-lived volcanism. If you have a molten mantle, like we have on Earth, the bit between the crust and the core, and if you have some upwelling in that that's stable over a long time, you have to have hot lava coming up, moving over, and then it has to go back down again. Just as we see air circulating in the Earth's atmosphere, you can get these long-lived convection currents in the mantle. If that happens for long enough, then you start to build up the crust at the point where you're pushing up mantle, and you don't build it up at the point where it goes down, and you get this dichotomy between the 2 hemispheres. So this is basically an imbalance in the interior of Mars. And that's what the Pathfinder results confirmed. They also talked about this region on the left that's in red here. You can see there are these 3 pimples on the surface. Those are the great Tharsis volcanoes. Tharsis, this region, is about 1 billion tons of matter lifted up above the surface to create 3 great shield volcanoes that dwarf anything we have on Earth. And next to them is Olympus Mons, the biggest volcano and the second highest mountain in the solar system. This thing is 22 kilometers from the base to the top, which is about 2.5 times the height of Everest. And the good news for anyone who's in the mood for an adventure is that it will be very, very easy to climb. So it's about a 4-degree slope all the way. So you can just walk up this thing if you have oxygen and patience. The bad news is that when you get to the top, there's no view at all. Because when you get to the top, the Martian horizon is so close that you only ever see the top of the mountain that you're standing on. So mountain climbing on Mars is a really stupid sport. Undoubtedly, somebody will put a flag on this one day, but they will have had a boring time. This is an enormous thing, and this and the Tharsis volcanoes cause a wobble in Mars's rotation, which we were able to pick up. And by studying that wobble, the mission techs were able to conclude that Mars has a solid iron core. So despite the fact it's a small planet, it has the kind of structure inside that Earth has. We can do a comparison of Earth on the left and Mars in the top right. You've got a large core on Mars, but not the fluid outer core that on Earth creates magnetic fields. So Mars has lost its magnetic field, and as a result, partly, has lost a lot of the atmosphere that it had in the early days. So that liquid water that existed in the first few billion years of Martian history has all more or less evaporated away. If you pour out a glass of water on the Martian surface today, it evaporates immediately because of the low air pressure. But there is a core down there, and that tells us about how Mars has formed. And we know more about that and more about the interior now because of a recent mission. So this is InSight. It was actually a rebuilt version of Phoenix. It landed in 2018. It's another static one. And I will read you the postcard from InSight before I talk about it. It says, where are we? Dear Earth, no wonder none of your fancy rovers wanted this job. This place sucks. There's nothing to see for as far as the camera can reach. There's just the empty plains and me. You told me to dig. Well, you should try digging in this stuff. The marvelous and expensive mole you've provided just keeps slipping out again. I have at least deployed the seismometer and can now spend sol after sol listening to the faint rumble of Mars quakes and, more likely, the wind as another dust devil rumbles past. I guess I'll hang around. I might dribble some sand on my solar panels for fun. They're not making a movie out of this mission, for sure. InSight. One of them had to be grumpy. But here's why. This is another selfie taken with the robot arm, and you can see it really is on a flat plane. I watched the NASA press officer put their head in their hands the night before landing when the principal investigator of this mission said proudly that they were landing in the most boring place on Mars. But it's boring for a reason. This is a geophysics mission, or I suppose because it's Mars, it's an aerophysics mission, studying the physics of Mars and its interior. And so you don't want any local distractions like valleys or hills or mountains or volcanoes. You need a nice flat plane. And then on that flat plane, you put a seismometer. So this is the deployed seismometer instrument that could detect Mars quakes, the equivalent of earthquakes, and then the cloche on top is to protect it from the wind. I'm particularly pleased to be talking about this one because the seismometer was built by some of my friends. It was led by Tom Pike at Imperial College, just down the road, and Neil Bowles and colleagues in Oxford built the electronics. We even got our logo onto Mars, which I don't think we were supposed to do, but I think looks great. This is actually a shot from the Martian surface. But before this seismometer got to Mars, of course, it needs to be calibrated, and the very first calibration produced some interesting results. So these are lab results from Neil's lab in Oxford. On the top here, this is time from left to right, and what you're seeing are detections of earthquakes and vibrations at different frequencies. And in the boxes in the bottom are two distant earthquakes in Chile and Indonesia that were picked up by this sensitive seismometer. But there's also in the top right, there's this long box that we can zoom in on, where you can see there are a series of quite rapid, short-lived vibrations that this thing is picking up. And to understand what these are, I need to tell you that this was Sunday morning, and that Oxford looks like this. And so these are the bells in the tower of Merton, Christchurch, New College, and the church on St. Giles in Oxford, each causing the floor of the lab to shake. So not only was this a good early test of the seismometer, the absence of such signals in the data from the Martian surface means I can be sure that there are no church bells on Mars. So this was indirectly a test for life. However, the other story I have to tell is that we did an event for the landing of InSight with some of my colleagues from Oxford and a wonderful scientist called Anna Horliston, who's from Bristol, who was working on this. And it just got across the human side of spaceflight. So we were all watching with a crowd of families and school kids and friends who'd come to watch. And we were watching Mission Control as they did the countdown as this thing hovered and slowly lowered itself to the ground on Mars. And I don't know what you'd expect from celebrating scientists, but it was pretty tense as this mission with all of this work and this one shot to land their instrument on Mars touched down. But it's Anna's reaction I'll remember, because she just went, "Oh, I've still got a job." And I think that's what we're talking about when we think about the human side of these missions. There are robots, but there's a team standing behind them. And Anna's job was to analyze the Marsquakes, and hopefully, this may or may not, no, okay, we've got plan B, don't worry. Pretty soon after the mission started, this will work, I think. Yeah, let's do that, and then that. Let's do that. Okay, so first thing, you're hearing the wind. This is 60 times speeded up. And then there's suddenly this shaking. And that's a Marsquake passing over the mission. So you can literally listen to these things. And then just as they were trying to record the end of that, the robotic arm moved to take a picture. So you can also pick that up. But this is evidence of Marsquakes on Mars. Some of them are native. They happen because of some remnant tectonic activity. So Mars is still active geologically. In fact, there's evidence that those big volcanoes are merely dormant rather than extinct. Sometimes they detected Marsquakes caused by meteorites hitting the Martian surface. And once they detected the landing of another rover, which set out a nice set of oscillations through the surface. And like on Earth, where people using seismometers can understand the interior of the Earth, on Mars we can use these measurements to understand the interior of Mars. So if we know the source,
this
we can
is
look at how these
space,
things...
and this is an...
Sorry, that's my fault. I'm just going to have to fix that. Sorry, 2 secs. This is now somebody dropping an egg from space, which is, who knows, perhaps the future of another Gresham talk. It's amazing what you can find on YouTube, alongside many other Gresham lectures. Good. Sorry about that. I wonder if he really did drop an egg from space. Tune in next week. What do they say? Like and subscribe. Yes, good. Anyway, speaking of eggs, Mars is in many ways like, no. So this is our model. So we now know there's a crust. We know there's a liquid core. We know the whole thing is slightly offset from the poles, which is interesting, and we get the surface. But there are results out this month that show that things are a bit more complicated, that there's evidence from these Marsquakes that there are lumps of material buried within the Martian crust and a little bit lower. Basically, Mars is lumpy inside, and what the interpretation of these results tells us is that it seems to be that early in Mars's history, like the Earth, it suffered a great bombardment of material. There were meteorites and asteroids raining down on the planet, and lots of those got incorporated into the planet. But on Earth, tectonic activity recycles this material. It disappears into the mantle, and we don't see it. In Mars, for a long time, there must have been no such activity. There's no evidence of plate tectonics on Mars, one of the great mysteries of the planet. And so we have this record of billions of years of impactors. It tells us that Mars, though it shows these small signs, it has Marsquakes and these volcanoes, it must have been inert for a long time. I'm going to briefly touch on Mars Reconnaissance Orbiter. This is a brilliant shot from its high-rise camera of Curiosity. Probe will come to in a bit, descending to the Martian surface. And the postcard says, "Dear Earth, wow, I love Mars. It's got magnetic dunes, craters, valleys, and old lava flows, and even the odd avalanche. I could stare at it all day. In fact, I usually do. But I do try not to have favourite places, although I like dark streaks on the northern plains. Could they be caused by flowing water or dust? Speaking of dust, let's hope the weather stays clear. We don't need a global storm. Thank you very much. Signed, MRO. Very boring, but, sort of effective. MRO could have a lecture to itself. In fact, I could stand here for an hour and just show you pictures from the high-rise camera silently, and you'd have had a good time. This is one from May earlier this year. It's exaggerated color, but this is the point on the planet where the Martian movie is set, Arcadia Planeta, where the Pathfinder rover touched down. And you can see the scalloped edge to the crater that tells us about the icy nature of the surface when something hit billions of years ago. And we can see processes today. This is false color again from 2011, but what you see here is an avalanche in progress on the Martian surface. And here are one of those dark slopes that I talked about in the postcard. These are often seen on sloping surfaces on Mars, these streaks that are hundreds of meters long. Some of them are long-lived, some of them repeat, some of them are not. Some of them just appear and then disappear. And they show up during the warmest parts of the year. And so for a long while, people hoped that what we were seeing here was liquid water, that some activity or perhaps just the heat of the sun had caused some of the permafrost to melt. You get a runoff and you get a streak. And maybe that's telling us that there's still water moving on Mars. Recent studies that use machine learning to look at where these occur on the surface suggest that they're actually probably dust moving down the surface. They don't show up on the steepest slopes, and they don't show up where there's ice. They show up where there are reservoirs of dust. But MRO has really given us the map that all the other rovers and missions map. Curiosity in 2012 was the first of the modern rovers. So there's the T-tray-like Sojourner. This isn't on Mars, by the way. This is in California. There's Spirit. Sometimes it's important to point out the obvious in these lectures. And there's Curiosity on the right. So we're up to things that are basically car-sized. Curiosity says, "Dear Earth, been busy doing chemistry since arriving here. That's what I'm built for. Everything you need for life is here. We found schnapps, sulfur, carbon, hydrogen, nitrogen, oxygen, and phosphorus in all sorts of combinations. And so this was not only a wet place once, but also somewhere where the ingredients life needs existed." I sang myself happy birthday one Earth year after getting here. Maybe a Martian year would have been more appropriate. I keep looking for the methane that you're so interested in, and it's odd. Sometimes I taste it, but sometimes I don't. What's going on? Curiosity. So just to explain those things a bit, I think we have to talk a little bit about the arrival. So Mars is tricky. So we've got NASA music on this one, which I might have a burst on. But Curiosity was too large to bounce down in airbags like Spirit and Opportunity did. Instead, once it had deployed its parachute and without its landing legs, it was then be dropped. It then flew on rockets for a short while. And then it was lowered down to the surface by what's called a sky crane, deposited gently, and then the crucial thing is that you have to hope that that orbiting platform lands somewhere else, because otherwise you just crush your rover. This worked. It was known as the 7 minutes of terror, but it delivered Curiosity safely to the surface, where it's been exploring ever since. It landed in a place called Gale Crater, an old lake bed, and it has been climbing the central peak of the crater, which you could see in that first top image in the distance. This is the triumphant mountaineering selfie on the bottom left, called Mount Sharp. And it's shown that indeed this was a lake that had warm conditions and a very rich chemistry. So the thing that's happened here that moves us beyond what Spirit and Opportunity have found is that the richness of the chemistry is evident. The happy birthday thing needs some explanation. After a year after it landed, the engineers worked out they could vibrate one of the instruments on the rover, and they did this to it. And they really, really did play that on Mars. Whether anyone was there to hear it, we're not sure. And they were. I get the feeling this is something a couple of grad students did, because NASA made a big thing about it, and then has spent years since explaining that they don't do this every year. But that's the only song ever performed on Mars, which is nice. Now, I mentioned methane. One of the things Curiosity wanted to look for is gas coming up from underneath the surface, because if you see something like methane being produced, then it's a sign that there's either a chemical process, perhaps some volcanism, or there is a biological process going on out there. And Curiosity found there's a seasonal pattern to the methane. It gets these burps of methane that tend to occur in the summer when things heat up, but occasionally, for example in 2013, it receives really quite significant amounts of methane. This is, the typical levels here are in fractions of a part per billion, but it got up to 21 parts per billion, which is quite a lot by the standards of these things. So there's something in the Martian soil producing methane, and we don't know what it is. Unless, of course, you read the Daily Star. Because after I discussed this on a radio program, this was the headline. Space boffins think tiny cows could be hiding under the surface of Mars. While there could be many reasons why Mars's atmosphere contains methane, that's good science journalism. Professor Chris Lintott from Oxford University said, that's not saying that it's not cows. And I stand by that. They'd have to be very small cows. But nonetheless, there's a possibility that there's a biological source of methane. And so what we'd want to do is take a global look at that. And that's where the awkwardly named ExoMars Trace Gas Orbiter comes in, a European mission which has been in orbit around the red planet since 2016. And TGO says, Dear Earth, firstly, my name's a bit of a mouthful. American rovers have positive sounding names, and at least MRO has something of a forward-looking feel. The European Space Agency's ExoMars Trace Gas Orbiter feels like a name decided by a committee, and I think TGO is a system for reviewing no balls in cricket. That aside, I've been observing trace gases in the Martian atmosphere. Oxygen doesn't really count, but I've called it glowing. And I've spent some time thinking about hydrogen chloride, and of course, the destruction of carbon dioxide. But what I can't see is any methane. None. Zip. Nada. And if curiosity is right, it should be there. Yours, ExoMars TGO. P.S. Where's my lander got to? TGO dropped off a little lander called Schiaparelli that crashed into the surface because of a software error on the way. It decided it had landed 4 kilometers above the surface, so it produced a very nice crater. But the salient point here is that TGO has found no evidence at all of methane in the atmosphere. And if methane is being produced at the levels detected by Curiosity, then we should see it. But we don't. So something or somebody doesn't make sense here. Either one of the teams has made a mistake, perhaps there's a contaminant on Curiosity, or perhaps the way that they're calibrating their instruments are wrong, or maybe TGO is doing a poor job of looking at the atmosphere and it's not as sensitive as we think it is, or there's something very confusing going on. And not only is something producing methane underneath the Martian surface, but maybe something's destroying it as well. We need a sink of methane. And I'm not saying that's cows with a degree in chemistry, but we can't rule that out just yet. This is a big puzzle. We don't understand. This would be a great end to the lecture if I could tell you what was going on here, but I can't, so I won't. We've no idea how to resolve these. It's an enormous argument. Which brings me to the last of the missions. This is Perseverance, and I think this is going to send us back to YouTube again, but that's okay. Perseverance landed in 2020 and was sort of a souped-up, rebuilt Curiosity. It landed in a place called Jezero Crater, and it sent back the following postcard. Dear Earth, Jezero Crater is fascinating. It appears a flood sculpted much of the landscape here in the distant past. I've had fun trundling around, pet rock on board for some of the time, and I know that the geologists on the team seem excited. The recent pictures of leopard spots were exciting. Are we seeing signs of life on Mars? I can't do much here other than tell you what I see. A proper analysis will require getting samples back to Earth. I've left several nicely stored and scattered around the landscape. When are you coming to get them? I'm a little concerned that I haven't heard from you recently. I'll keep going in the meantime. Clues in the name, Perseverance. So this is the difference between this rover and all the others. Suitably sort of American work ethic there, I think, which is nice. It's in a river valley. There was water flowing across this landscape. You're looking at a delta here that was last active about 3.7 billion years ago, and the images are fantastic. But Perseverance's mission is a bit different. Rather than just analyze in situ, what it does is it takes samples. So this is an example of a sampling mission. So it drills down a little way into a rock, and it pulls back a small tube of material. This is the current Perseverance rock collection. So there are 33 samples here, plus a few empty ones that have Martian atmosphere in. And these things are deposited on the Martian surface. Some are kept on the rover, and some are dropped off. And the idea was that in a future mission, we would send rovers to go and collect these things and then bring them back to Earth, because the kind of analysis that we want to do requires being here. For example, this summer, much was made of this image. This is part of the surface imaged by Perseverance, and down the middle you could see what are called leopard spots, these small circular features. Now on Earth, if I showed a geologist this rock, they would tell you that the process that produced those was life, that it was bacteria interacting with the minerals to produce these sort of round spots. It's a giveaway that life has interfered in your geology. So then the question is that's what's happened on Mars. Are we seeing here evidence of ancient life or even current life on Mars? Well, it's very difficult to say. We have time to play with on Mars. This could be an obscure process that takes billions of years that we have no terrestrial analog for. This may be a false positive. Maybe it's just some bizarre water-deposited features. What we need to do is get this rock, or a sample of it, back to the kind of laboratory we can put in a university, but which we can't put on a Mars rover. And that's why these samples that Perseverance have created are so important. They are little time capsules of this fascinating place that we know had all the ingredients for life, but which we don't know the details of the history for. And here's the thing. At present, I don't think anyone's going to go and get these. Despite the fact that Perseverance was launched with a clear plan for a follow-up mission, there's no money. There's no will to go and collect these time capsules and bring them back. And so while agencies are still studying the possibilities, it's likely, I think, that in 10, 20 years' time, these things will still be on the surface. Science that we're not able to do because we lack the imagination to go and get them and bring them back. And so we're at this tipping point, 50 years after Viking, where we have to decide what the future of Martian exploration is. Are we actually interested in trying to take the many different threads that I've touched on tonight and turn them into one story of our neighboring planet, which will be rich and fascinating, and in some places Earth-like and in some places not? Or are we going to go back to seeing it as a place that one day perhaps a billionaire's boots might touch, but which no one would do the science? Mars, I think, and how we think about Mars tells us a lot about how we think about our place in the solar system. It's a fascinating, complex, confusing, mostly red place, and I hope you've enjoyed hearing about it. Thank you very much. Thank you.
I don't know about you, but for me, there are certain things I remember from lectures, not necessarily the contents, because part of the academic team, we get to see the text and the presentations beforehand. A few lectures ago, it was the circle was added later.
Oh, yes. Yeah.
And today it was this no view from the top, which is like so depressing.
Yes. Yeah, mountain climbing on Mars is merely for ego, I'm afraid.
Yeah. So we've got time for questions. If you'd like to raise your hands, there will be 2 microphones going around. Shall we maybe start at the front? Just one second, my colleague Jeff is coming.
Hello there.
Hello. The picture of the interior of Mars, the cross-section,
yes.
I was surprised to see that it showed the liquid core. Was that the early Mars, or does it really still have a liquid core?
So we don't know. So what we know isn't, so on Earth you have a solid core surrounded by a fluid outer core. What we know on Mars is that we have a large core, but its state isn't well understood. So one of the things is that it was colder than the Earth's core, because Mars has lost more of the internal heating that comes from radioactive elements than the Earth. So there's some possibility it's fluid. What we need to do is have a very long-term experiment to look at the rotation of Mars and how it's changing, and that will tell us that. So I think that's an open question at present. One of the problems is we don't know what it's made of. So going from the measurements we can make to a size and whether it's solid or fluid depends on the composition, and we don't know the composition of the core. So yeah, that's an open question. Thank you, though. It's important to point out.
There's a question from Dave online. You're given a massive budget to develop your own Mars lander. What form would it take, and what experiments are on board? P.S. Loving the postcard.
Good, thank you. Massive budget. Let's have £1 billion. That'll do. So that's not enough to go and get those samples. We think that's about a 5 billion mission over 20 years. So it's, if you work it out per year, it's pretty cheap. It's about a Mars bar per person in Europe and America. I think I want to go back to the fact we've only explored 10 places. I think I'm going to spend my massive budget on a whole load of quite cheap probes, but maybe 200 of them. And they're going to be so cheap that half of them won't work. But then I've got 100 new scientific stations on the Martian surface. And then I can sort of do the global physics, like just doing a global weather network would be hugely useful from the surface. So I think I'm going to just pepper the place with tiny probes and hope that some of them work.
Maybe an idea for next year's Christmas fundraising
Yeah, that's right.
appeal.
If you donate to my
5
Mars
billion.
program this week.
Are there any more questions in the hall? I can see here, a gentleman here. Jeff, could you maybe?
Oh, we're going just here,
Yeah,
I think.
it's coming,
Seeing
it's
the
coming.
microphone's coming to you there.
Okay, well, thank you very much for the lecture. Again, I love the postcards as well. As much as I love the little rover that could, my question's about the Viking missions, which
Yes.
are searching for life. So how were they able to, avoid the risk of, how were they able to determine that, if they did find anything, it would not be a contaminant already inside the, the probe itself? And also, of course, the idea that in our quest to find life on Mars, we may have seeded mostly expired biological material.
Yeah, these are really good questions. So the simple answer for Viking is that people worried about this much less in the 1970s. So, for example, it was just assumed that the journey to Mars would kill off any bacteria. We now know that's probably not true, or at least it may not be true. For example, there have been extremophiles found living on the outside of the space station. You can also ask the question, if you take sort of the extreme bacteria from Earth that live in, say, the Antarctic dry valleys, and you expose them to Martian conditions, they do okay. And so this was a worry. And in some sense, the fact that the biological experiments on Viking didn't detect anything tells you that actually nothing made the trip. There are particular worries about prior Russian attempts to land, where there were Russian probes that crashed into the surface. Those weren't decontaminated at all. And my personal hope is that if we do find life on Mars, let's say we go and get these samples and there is a viable biological activity, I really hope it uses different base pairs in its DNA compared to Earth, because then you'd know it was different. The problem is that Mars and Earth have been exchanging rocks for millions or billions of years. In fact, there's this weird paradox that probably the oldest bit of Earth that exists is on the surface of Mars. We'd never recognize it, I don't think. But there is an exchange between the two, and so if you believe bacteria can live for a long while in space, maybe millions of years, then the two will be connected anyway. So this is a hugely complex problem that I think we should worry about once we've found life. But you're right, that once you've found life, the next question is it independent? The importance of life on Mars is that it tells you if life got going independently twice in the solar system, then it should be common in the galaxy. But to make that statement, you need to assume it's independent. So that comes later. I'll spend my second big budget on that once I've found the aliens.
Well, question from Anonymous. How far are we technologically, as opposed to having the will or money, to putting a human on Mars?
I think if you wanted to do it in 10 years' time, and you were able to accept a huge amount of risk, and you didn't care about whether you had a good time or not, I think you could do it.
Is that your retirement plan?
Sorry?
Is that your retirement plan?
No, I mean, I don't credit Musk with much, but his retirement plan is he says he wants to die on Mars but not on arrival, which seems fair enough. The truth is it's always going to be a much less hospitable place than Antarctica, and the problems of getting there are one thing. You've got radiation pressure, especially if you're on the surface, so you're going to end up living on a cave while you're there. But I think the big unsolved problem on Mars is this dust that's everywhere. It's going to get everywhere. We know that very fine particulates are very bad if you breathe them in. And I actually think the big unsolved problem of living on Mars is how you filter the dust out of your environment. Because once it gets into your nicely sealed habitat with recycled air, then I think you're in trouble. So I think if somebody wants to go and plant a flag in 10 years, they probably can. I don't think they should, because until we know the biological status, don't think we should be putting humans down there. Whether anyone will or not, I don't know.
one last question, maybe from this side from the hall, just to make it fair. Yep, microphone
While
is
the
coming.
microphone's moving, I'll
I think
just tell
there's
you
one here in the middle.
briefly the story of, I met a man once who was promoting within NASA what he called Project Eagle, which was a budget mission to get somebody to Mars, and Project Eagle had a brochure with somebody planting the American flag on Olympus Mons, oblivious to the lack of view. And Project Eagle's slogan was one man, one vision, one way, because it's much cheaper if you don't want to come back. I don't think it went anywhere. Yeah, sorry, there's a question there somewhere.
Yeah, hi. I was wondering, does the chemical composition of the rocks that we find, for example, in the spheres on the berry bowl, for example, does the composition of them in different parts of Mars suggest the rate at which water disappeared? And can it kind of show you which parts had water for longer?
Yeah. Yes, so we are beginning to put a sequence together. So for example, that acidic phase came after the warm, wet, neutral phase. And there do seem to have been differences between bits of Mars, both on a global scale. It won't surprise you that this is the low-lying north. That was probably a global ocean for a long period of time. The mineralogy tells us that compared to the highlands, which were much less so. But there is also evidence of late water in some places that people argue about. And really, we only properly understand 6 or 7 of the 10 sites we've landed in, and we can tell their stories, but they don't quite add up to a global picture yet. So I can't tell you that the ocean lasted for 1 billion years and then it faded, and then we had lakes in the south and so on. But there's complexity here. And the fact that Curiosity and Perseverance have spent more than a decade and 6 years respectively exploring one site and piecing together the geological history shouldn't surprise us. If you're a geologist on Earth, you do a whole PhD on one valley or one place and being in the field and trying to understand that. So we're just beginning that process. But we have tools because the minerals record this history. And on Mars, they hang around. So you don't have any of this pesky life that destroys nice geological evidence. And you don't have plate tectonics. So we do have the whole history of the planet there written out for us. And that's one of the reasons it's compelling. We can tell the long story of Mars in a way that we can't tell the long story of Earth from direct observation. But thank you for the question.
Yeah, thanks for your questions, and thanks you for coming or watching online. Next lecture will be on the 4th of February, Alien Earths, What Makes Us Special. Do you want to give us a sneaky preview?
Yeah, it's the same thing, really. So you go to Mars because Mars is not Earth-like. Next year, we'll discover our 10,000th planet around other stars. I want to talk about the ones that aren't Earth-like and what we learn from them.
Thank you very much.
Thank you. Take care.